Think Geek magazine. Let's see what's new. We got some Star Wars stuff, Big Bang Theory stuff, a Star Trek pizza cutter. Hello?
Allie, help us.
What? You need help on bonding?
Yeah, bonding. Hey, you.
I'll be right there! To the lab! Have no fear, the chemistry nerd is here!
Oh my gosh, we don't get this.
Help us, chemistry nerd. Help us.
Please.
Good thing I brought some friends along to help. Let's talk about the basics. Valence electrons. When you draw a Bohr model, like I have, the valence electrons are on the outermost layer of the Bohr model. We're going to know to explain the octet rule, which I'll let my friend, the professor, to explain.
The octet rule states that each atom needs to have a full outer layer of electrons like a noble gas. To obtain a full outer layer of electrons, the atoms bond together.
Now let's talk about ions. Ions are atoms, or a group of atoms that have a positive or negative charge.
I have all these electrons. I wish someone would take some.
Hey, give me some of the electrons.
Whoa, whoa, whoa! It's a K-cat ion. He just wants some of your electrons that you don't really want anyways. Here, put the gun down. Violence is never the answer. Now, cation. Don't you feel more positive now that you've lost some of your electrons?
Yeah.
So, anion. Now that you've gained all of these electrons, how do you feel?
Feeling pretty negative.
Why?
These are heavier than I expected.
Silly anion.
A binary compound is either an ionic or molecular bond that involves exactly two different elements. Not 3, not 4, not 15. 2 elements.
Now let me introduce you to one of my friends.
My name is Bond. Ionic bond. I kill people by day and bond with metals by night. I like my electron taken, not shared.
Us ionic bonds are the strongest of the 3 bonds. I interact with both metals and non-metals. We're crystalline solids at room temperature, have a high melting point, and conduct an electrical current when dissolved in water. Name ionic compounds. What you first have to do is name the cation like normal. And with an anion, you have to take off the ending and add "-ide" if it is no polyatomic, but if it is a polyatomic, you have to add 8. Sodium chloride, it is no polyatomic, and this is sodium chlorate, which is a polyatomic.
Let's see what the covalent bonds are doing.
No.
No, they're mine.
Guys. Peace, love, and electrons. Just share them.
Oh.
The diatomic 7 are the elements that exist naturally in pairs.
Covalent bonds have low melting points.
Between covalent bonds, there are single bonds when they share 2 electrons, double bonds when they share 4 electrons, triple bonds when they share 6 electrons. When they form these bonds, certain orbitals overlap. In a single bond, the s orbitals overlap, forming a sigma bond. Double bonds have 1 sigma and 1 pi bond, which overlaps the p orbital. And the triple bonds have 1 sigma and 2 pi bonds, which also overlap the p orbital.
Each type of covalent bonds is the coordinate covalent bond. These are bonds where one atom contributes both bonding electrons. This is an example of a coordinate covalent bond where this pair of electrons is transferred to the carbon. As you can see here, this is the result.
To name covalent bonds, like H2O, first start off with the first element, which is hydrogen. You use the same name as hydrogen. If it has more than one of the elements, like the H2O has 2, you add a prefix, so it would be dihydrogen. For the second one, you add the prefix, and since it has one, it's mono. Instead of saying monooxygen, take off one of the O's, so it would be monoxygen. But then you chop off the ending and you replace it with an "ide." So it would be monoxide. So when you put it all together, it's dihydrogen monoxide.
The metals in the D block don't have a set charge. So to find out what their charge is, you look at the anion. In this case, phosphate has a charge of -3. So since one nickel is paired with a phosphate of charge of -3, nickel has a charge of +3. So it is written as nickel 3 phosphate. Some compounds form acids, such as these here. If the hydrogen just bonds with one element, you add the prefix hydro and the suffix ic. So in this case, since hydrogen is bonded to sulfur, this is called hydrosulfuric acid. If the hydrogen bonds to a polyatomic ion, use the suffix ic. So this would be sulfuric acid. If it's one less oxygen, use the suffix us. So this would be sulfurous acid.
Let's see what the metallic bonds are doing, shall we?
Whoa, it's like a sea of electrons.
Whoa!
Far out.
Peace, love, and electrons.
When metals bond together, their electrons flow freely together in a sea of electrons. Metals are ductile, so they can be drawn into wire, and are malleable, so they can be changed into other shapes easily. What's cool about metals is that most of them form alloys, which is bonding between different types of metals to make them stronger. When iron, chromium, and cobalt bond, they make an alloy called spring steel.
The Vesper theory states that the lone pairs on the central atom want to be as far away from the other electrons as possible, forming different shapes in the bond angles. Different steric numbers form different shapes, as seen on this chart. A steric number can be found by adding the number of atoms bonded to the central one, in this case it's 2, and then adding that to the number of lone pairs, which is also 2. So the steric number of this molecule would be 4. Chemistry nerd can tell us what kind of shape this molecule is.
Using this lovely chart, it is bent.
Hybridization is when the orbitals are smushed together to make hybrid orbitals. The steric number can be used to find the hybridization, as seen here. A bond is polar when the electrons are not shared equally between the two atoms, like HCl. An easy way to determine whether or not a molecule is polar is by using the electronegativity chart. If you subtract the numbers from the two atoms and the difference is greater than 0.4, then the molecule is polar. If it is not greater than 0.4, the molecule is nonpolar.
So an exception to this rule is if the molecule is symmetrical, the electrons are being pulled equally and it becomes nonpolar. Dispersion forces are between two nonpolar molecules and is the weakest. Dipole-dipole is between two polar molecules and is stronger than dispersion. Hydrogen bonding is the strongest of the intermolecular forces. It's when hydrogen bonds with nitrogen, oxygen, or fluorine.
Network covalents, such as SiO2, are the strongest of all the bonds. Then ionic, metallic, hydrogen bonding, dipole-dipole, and dispersion forces.